Every real analysis course begins with a presentation of the real numbers, the set of real numbers, the one thing that we portray as a straight line in calculus. And there are two approaches in which this presentation can occur. The first one is just to state some basic properties of the real numbers and the set exists and it satisfies all of these properties, which we will be calling axioms, the axioms of the real numbers. And if you look through them, you will see that most of them are pretty obvious and arithmetic in nature. For example, the fact that addition is associative or that multiplication is commutative. Someone looking at them and reading them in this order will say, hey, I do agree with these. Q also has them, the rational numbers. Then there are some axioms related to the order on R. For example, if you have two positive real numbers, then their product will also be positive. But after you finish up reading all of these arithmetic properties, you will stumble upon this property or axiom called the axiom of completeness, which tells you that every subset of R, which is non-empty and bounded above, that means that you have an element that is bigger than everything in the set, must have a least upper bound. That is, out of all of these upper bounds that exist as because the set is bounded above, you must find one that is the smallest of all of them. And you say, wait, well, I can technically picture this because I've done some calculus in my time and I've seen that you have the real, you have the straight line, which is represented by the real numbers, so that if you take any subset of the straight line which has a type of a boundary there, then there must exist something that is the smallest boundary, if you want. Yeah, but isn't analysis supposed to be the foundation of calculus? Shouldn't you believe that the set of real numbers is a straight line because of this property, not the other way around? So you see the problem here. Hence, you can already identify some issues with the axiomatic approach. First of all, we just say that R exists, which is a problem on its own. We don't know that. Of course, R could be the empty set. The empty set could be the only possible set that satisfies all the arithmetic properties plus the axiom of completeness, because we know that Q satisfies the others, the arithmetic ones, but that doesn't mean that already from this you can say that there is a set that satisfies them all plus the axiom of completeness. That's the first issue. The second issue is this weird thing called the axiom of completeness itself that should supposed to tell us that the real numbers represent a straight line. So in that regard, how can this one axiom tell you that R represents a straight line? That's the second issue. And finally, the third issue, does Q also satisfy this axiom? And in some courses, Q is proved to not satisfy this axiom, and that's very helpful in a way, but you also should see a picture of Q, because Q almost represents a straight line. It's almost there. But you should also see the picture that Q actually represents in order to see why it isn't a straight line. So these three issues, all of them, are resolved with the second approach, and that is to construct the real numbers, to give you an example of a set that satisfies all of these axioms and is not empty. And that is interestingly done from Q. Q can be, I guess, transformed, or it can be used in the construction of this set that I can state and define to you. I can put it right here on the screen and prove to you once and for all that the real numbers is not a theological invention. This is the main objective of the series of videos that I plan to make. The first of these videos, which is this one, has to do with the motivation behind this construction. Basically, why Q isn't enough. we will be able to see the intuition and the picture that Q actually represents and how it isn't a straight line. The second of these videos will have to do with the construction itself and how we can actually define the real numbers, technically kind of like the most important video of the series. Plus, we will also define the structure on R and restate, I guess, the properties that it should satisfy. And finally, in the last video, I will give a rigorous proof of one of the properties, one of the most complicated properties, that I think gives you more intuition on why you should portray the real numbers as a line more than an arithmetic construction, and why geometric intuition should be used in every proof that you do in analysis. It's fundamental, it's very important. So because I know this is important, the two objectives that I have in this series is just to give you the proof that R exists out there, which mildly can be acquired by looking up in every book on the subject. But the second objective is to justify this whole geometric intuition that you should have in every proof for analysis. Because if I can do it, of course, so can you. So without further ado, let's get into more details on paper. Okay, so as a beginning, I have listed here all the properties that the set of rational numbers, along with the addition defined on it and multiplication defined on it, as well as order, should have. So if we look strictly at them, at least F1 up to F9, we notice that they are kind of trivial, and we kind of assume them as being obvious every time we do things with numbers. So for example, we assume that addition is associative, that addition is also commutative. It has this 0 such that R plus 0 is equal to R. And every element of Q has an opposite element called minus R, which if added to R will equal 0. And the same things basically happen for multiplication, aside from the fact that every non-zero element of Q has an inverse. So I'm referring to this property here. Yeah. And of course, F9 is the distributive law. Yeah. So these are kind of obvious, and you can agree in a way with them more than you can agree with the last property that Q might or might not have. So that property is called the completeness, and R has it, but Q doesn't. So in a way, R should have all of these properties, F1 up to F9, but also should have another property that I will write in a bit. So aside from F1 up to F9, we also want R to have an order defined on it. This is not an operation, this is a relation defined on Q. That means that every two elements in Q are related to each other in a way. I mean, they either are related or they are not related. So the first two are kind of intuitive, but they are mixed properties. They say that this relation, this order relation, should be compatible with the operations that we have defined. That means basically O1 and O2. These are again kind of obvious for someone who has worked with numbers before, especially O2. And they have a little bit of a subtlety, a subtle flavor of geometry behind them. They are not strictly arithmetic because, of course, the relation itself can be thought of geometrically. So if I have this line here that we will see is not equivalent to Q, but for the sake of argument, let's say that we are naively believing that Q represents straight lines, and we put R here, then of course S, if S is less than or equal to R, they are related in this way, then S can't be anywhere to the right of R. So therefore, So therefore you have this geometrical picture of S being only to the left of R. So you have this subtle geometric flavor behind the relation itself, right? And finally, O3 here is a strict property of the relation, of the order relation that we are talking about. And it basically says that any two elements of Q are related by this relation. Yeah. So for someone who hasn't seen orders that or order relations that don't have this property, it might seem very weird to picture them or to see how a set that doesn't have such a property looks like. Well, imagine it this way. So if Q didn't have this property, I could take at least, so, and of course we are naively believing that Q is a line. We are taking it like this, and we have this R here, and we also have this S, such that neither S is less than or equal to R, nor R is less than or equal to S. So where can we put this S? We cannot put it to the right of R, nor to the left of R, because that would imply one of these. So what the idea that mathematicians do is to put S here, above R, basically, right? So that these two elements are not related in any way. This is a little bit of a stretch of what a Hasse diagram should look like. So I encourage you to look up what a Hasse diagram is and to think about what this is and how can a set not have this property, because it's very, very interesting one way, and it also gives you a motivation behind why Q has this property and why it's important and should be stated. Okay, but what's the problem with Q in general? Well, I have drawn here our naive image of Q, as we can see the line, but I have also drawn 2 points on Q, right? 1 here and 0. And I have elevated this distance up here, and I have drawn a square or half of a square to represent this distance that is root 2. Notice that this is a distance that we can reflect by drawing an arc of a circle here on our line, Q. This distance is a real one. It can be drawn, it can be viewed in real life. So if this distance here from 0 to root 2 is a segment of a line, then it should be on the line. That means both what's in between these 2 points should be in Q, as well as the boundaries, these 2 points, 0 and root 2. Right? This is root 2 because of the Pythagorean theorem, of course. But here, if you have seen a proof that root 2 is irrational, you see a problem. That this point does not belong in Q, which means that here is a pinhole. And our image, our naive image of Q as a line, falls down. So if we are to imagine this set Q as a line, we should also point out when do we have these pinholes here. Where do we have them? So root 2 could be the only one, but we know, of course, that that's not the case. Root 3 is also irrational, so it doesn't belong to Q. So we have another pinhole. So this whole image that we have drawn here is wrong. It's not true. Q shouldn't be portrayed as a line unless we put these pinholes in place. So we have to complement our image with these weird points that don't belong to Q. And you see why we need to construct R now, because this whole thing that we did with the square, we created this pinhole, and we can definitely create the other pinholes in a similar way by doing something to Q. we basically created this square by doing some operation on Q and effectively created something that is not in Q. So in a way, Q has the problem that a certain operation, let's call it circle defined on Q and Q with values, well, we hopefully have these values inside Q. Let me switch to black actually. Such that this operation when taken on the point 1, 1 from here equals something that is not in Q. So we have the problem that when defining these operations, they take elements from Q and throw them out. They just fly out, right? So that's the intuitive problem of Q, but how do we solve it? Well, let's look at the problem in this way. So the problem really is that between any two rational numbers, like let's say that we have 2 here, around here, yeah? Between 1 and 2, which are rational numbers, we have one pinhole, at least one. Well, the other ones are basically constructed in a similar way, but as you can see, root 3 is also between 1 and 2, so we have 2 pinholes. We actually can prove that we have an infinite amount of pinholes, but I'll just skip the details for now. But one pinhole is problem enough. So at least if we can solve one problem, we can solve the finite problem and then work on the infinite problem. But how do we solve it really? Well, to look at every number between, for example, I don't know, all elements that are less than this pinhole and 2, we just have to define a set. So we define this set that goes from 0 to root 2, but without including root 2, so that we make sure this set is a subset of Q, right? We define this A as R from Q, such that R squared is not less than or equal to, but less than 2. And I guess R is greater than or equal to 0. Because if we don't impose this, we are looking also at these elements. So we have this set, right, that includes everything here. So everything until we hit this pinhole here. Okay, great. We also look at something interesting, that this set has an upper bound. So 2 is an upper bound of A, right? It surely looks that way because 2 is greater than anything in A. So then we might ask, how many upper bounds does A have? Well, of course, an infinite amount, but how many are here? Between this 2 and the pinhole that is root 2, right? How many? And in that regard, we ask, does A have a small, not a small, a least upper bound? That is, looking here from 2, we get smaller to, I don't know, 2.1, maybe get to 2 or 1.8, so on and so forth. But at some point, I will have this question in mind. Hey, wait a second. But what's the smallest upper bound of this set? Well, there isn't any, because that one is root 2. So for any upper bound of A, there will always be a smaller upper bound of A, and that one won't be root 2, because root 2 does not belong to Q. Okay, so here are some interesting insights regarding Q, because now we know that Q doesn't have the following property. for any A that is a subset of Q, and of course A is not the empty set, and A is bounded above, then let's say that A has a least upper bound. We call it S from Q, such that S equals sup A. Supremum. Sup comes from the word supremum. Okay, so we know now that Q doesn't have this property, and by not having this property, it fails to be a straight line. So therefore, we have to find a set that has this property so that we can picture it as a straight line. And that's the motivation behind constructing the real numbers. Okay, so this concludes the first part of this series. I really hope I have piqued your interest and your appreciation of this whole journey in a way, and I will hopefully see you on the second part. Thank you for watching.